True quantum computing is trapped behind a wall of liquid helium. The hardware requires sub-zero temperatures and million-dollar laboratory setups to maintain a stable state. That extreme environment creates a severe bottleneck. It keeps the ability to test, iterate, and experiment out of the hands of everyday developers and edge computing startups. Today, we are looking at a proposed workaround, the QX-bin framework. We are going to bypass the deep mathematical proofs to focus purely on how this framework applies as a physical and digital tool. The core concept here is personal qubit simulation, or PQC. It is the idea that you can map and simulate complex quantum logic directly onto classical, room temperature hardware. The value of QX-bin lies in its accessibility. It gives users a way to experiment with multidimensional states without needing a massive research budget. To understand where QX-bin fits, look at this quadrant chart comparing accessibility versus quantum accuracy. In the top left, traditional mainframes offer true entanglement, but zero accessibility. In the bottom right, QX-bin operates on standard machines, trading physical qubits for mathematical simulation. Since QX-bin is a simulation tool, the question becomes, what does applying it actually look like in the real world across different disciplines? Adopting QX-bin means deliberately sacrificing enterprise-grade quantum processing speed. In exchange, you get a simulated probability matrix that you can actually touch, code, and deploy. The first path for deploying this framework is hardware prototyping, aimed directly at makers and physical engineers. This route starts by utilizing analog Hall effect sensors to measure the physical probability of an unpredictable event, like a coin wobbling in midair. Instead of just recording a final heads or tails, the sensors map the analog nuances of the coin's trajectory, translating that continuous physical wobble into a readable state. The outcome is a hardware interface that records these superpositions at room temperature. As detailed here, it relies on a grid-based punch card system printed on magnetized paper. You can see the intended contrast with traditional computing in this diagram. The top shows a standard linear binary chain, while the framework below maps out a clustered spatial quantum chain to handle the data. The trade-off here is steep. This route demands significant mechanical engineering, and your accuracy is entirely bottlenecked by the physical tolerances of those analog sensors. Hardware makers must weigh that intense fabrication time against the unique pedagogical value of physically translating analog probability into a digital matrix. The second application path is the digital route, software implementation, designed specifically for developers and data scientists. Instead of building magnetic grids, the input here involves writing classical code arrays that implement QSpin's mathematical structures to simulate multi-qubit states. The foundation of this software array relies on what the framework calls fractional bases. Looking at the formal definition, you can see how it uses ratio placeholders to symbolize directed basis contributions toward the 0 or 1 states. Coding this math results in a fully functional, mathematically normalized simulator. And because it is a classical simulation, it runs entirely on standard desktop CPUs. This gives developers an immediate way to test quantum logic and probability conservation locally, bypassing the need to pay for cloud access to a physical mainframe. However, because it is strictly a classical simulation, it scales poorly from massively complex algorithms when compared to true quantum hardware. Software engineers should utilize this specific application for learning Bell states and quantum logic natively, as it lacks the processing power to crack enterprise-grade cryptography. The third and final application path takes the framework to the street level, commercial edge integration, specifically utilizing the pikk model. In this context, edge computing means taking processing power out of centralized server farms and deploying decentralized data pods directly into physical community spaces. The required input involves retrofitting underutilized real estate, like street kiosks and vendor stalls, with clean energy, IoT sensors, and local processing hubs. The outcome is a localized network. These edge hubs can process AI and simulated quantum data instantly, giving micro-entrepreneurs powerful tech tools right on the street corner. It is an ambitious community goal, but it immediately collides with the reality of physical infrastructure. Deploying this network requires massive logistical investment. You have to navigate commercial real estate zoning and deal with local power grid limitations, challenges that go far beyond just understanding a software framework. tech integrators must approach this route as a heavy infrastructure and real estate play that demands physical logistics and power management. Looking at this comparison table, we can bring all three of these application paths together to clearly map their demands against their deliverables. The realistic outcome column maps everything from tactile physical punch cards to localized data pods running in the community. But the primary trade-off column grounds our expectations. Every path carries severe limitations, whether that is mechanical bottlenecks, classical scaling walls, or massive real estate hurdles. Ultimately, Cube-INX is a tool for simulating and interfacing with probability at the edge, even while remaining bound by standard classical hardware limits. To decide your exact next step, we can use this final flowchart, mapping your specific goals to a deployment path. If you are a student or a data scientist whose primary goal is understanding quantum logic quickly and cheaply, skip the hardware. Stick exclusively to the Python application. If you are a hardware maker driven by building novel, tactile interfaces, mapping out that Hall effect magnetic grid is your ideal project. And if you are an enterprise developer who needs true exponential quantum speedups to run complex algorithms, you should avoid the QXBin framework entirely. Matching the right QXBin application to the right technical background is the only way to get functional results from personal qubit simulation without wasting resources.